Okay, so I want to now use the holonomic approximation lemma to do some stuff. I have written down here the statement of the holonomic approximation lemma and the local relative version. I managed to convince Kai that it works, so it's good. So he doesn't have to retract his own book. The pink is hard to read. Okay, well then forget about parameters because it's too confusing anyway. Just don't look at the pink and look at the white. Okay, so again, what's the idea? I have a subset of polyhedron of positive codimension. I have some section, and then the claim is that there exists smooth isotopy such that in a very small open neighborhood of the wiggled polyhedron, there is a holonomic section which is C0 close to the original one. Okay, and then we can have all kinds of enhancements. And again, just because I think the main geometric idea is not so hard to understand, let's again think of this problem of going up a mountain, right? So again, if I have 2 points, but we can do it for any, you can think of that case, but let's do it for any section. I have 2 points, let's say that are delta apart, okay, and so therefore I have 2 Taylor polynomials, H1, H0 and H1, then H0 minus H1 will be O of delta apart. So of course, if I try to interpolate in this direction, then I will get an error in, let's say, first derivative, that is O of delta over delta, which is 1. Okay, because that's how much energy, that's how much error I spend going across delta. But if instead I interpolate over, let's say, some epsilon distance, okay, then the error in the first derivative is O of delta over epsilon, as a straightforward computation shows. And in fact, in the rth derivative, the same computation shows O of delta over epsilon r. So as long as you pick your construction with parameters so that this quotient is sufficiently small, you can achieve your holonomic approximation by interpolating from this one to this one in this direction. And now I can interpolate to the next one, and so on and so forth. And that way I construct the holonomic approximation. Okay, so I've just repeated what I said this morning, and now I actually want to extract some consequences to geometric topology. Any questions or anything else I can say at this point, so that we're all happy with the statement of the holonomic approximation lemma before we proceed?
Careful, can I do net guess as well? Right, there's no bound on R.
I'm not sure about that. At least the calculation wouldn't suggest so. I don't know if anyone has a different opinion, but my impression is, at least the proof as I know it, doesn't work. Does anyone think otherwise? Yeah, it's an interesting question. Okay, so let's do some stuff. So consider the space of emergence from a manifold into another manifold, which is a set of smooth maps with injective differential. And when I say injective, of course, what I mean is fiber-wise injective. Okay. I also want to consider the space of bundle monomorphisms. Okay. What I mean by this is maybe what Alvaro would mean sections of this, but I'm just going to say exactly what I mean so there's no confusion. So this consists of some bundle map covering any smooth map. So let me emphasize that this is any smooth map. Such that, again, the collection of fiber-wise linear maps is injected. Okay, so this is an immersion. This is a formal immersion. I have decoupled the map F from its derivative capital F, and I have no requirement whatsoever on little f, and I have put in the differential relation. So
if it's any smooth map, there's no obstruction within it.
yeah, to the little f, there's no obstruction, but to the big F, there is an obstruction. Right. Okay, and so now let's prove. I want to prove the following two theorems. First theorem: if M is open for concreteness, okay, let's think M is connected and either non-compact or with non-empty boundary. Then there is a derivative map that takes F to the formal solution where capital F is the derivative of F. And then the theorem is that this is a weak homotopy equivalence. So it induces an isomorphism on all homotopy groups. And then the second theorem that I will prove is that without any assumptions about M being open, but if the dimension of M is strictly smaller than the dimension of N, then the same conclusion holds. Although actually in this case, a slightly stronger conclusion holds, but let's stick with this for now. Okay, so this is the Smale-Hirsch immersion theory. Any questions about the statements of these theorems?
The second one, it can be closed.
Yeah. Second one, so in the first one, the dimension of M can be equal to the dimension of N, but I demand that M is open. And in the second one, M could be closed, but it must have dimensions strictly smaller than the dimension of the target.
If you wanted to state a relative version of that, do you have the codimension restriction?
Yeah, so that's why I was saying that this one holds in a slightly stronger version. So here you are going to get relative and C0 close, etc. And in the open one, you have to be, there's something you can say, but as stated, I can't. Yeah. More questions? Yeah.
What is WH?
Weak homotopy equivalence means that it's just an isomorphism on all homotopy groups. More questions? Okay, so example, what are the immersions of a circle into R2? Well, this is weak homotopy equivalent to bundle monomorphisms of TS1 to TR2, okay? And R2 is contractible, so there's absolutely no information in the underlying map from S1 to R2. So the only information is in the bundle map from TS1 to TR2, and you can convince yourself that that is going to be equivalent to O2. Going to be equivalent maps from X1 to O2. or even to maps from the circle to the circle. Okay, and so what is pi 0 of the space of immersions? Well, it's Z, and that's the turning number that Melanie was talking about. Okay. And each component has the topology of S1, because given any map from S1 to S1, I can change where the base point goes, and that gives me an S1, and there's nothing else. So this is the topic to the Z's worth disjoint union of S1s. Example, so let me just say, Smale's sphere version, the fact that you can avert a sphere, I'll leave it as an exercise for you to deduce it from the fact that pi 2 of SO3 is trivial. Okay. Pi 2 SO3 is trivial will tell you that the two formal classes of the sphere and the sphere inside out are the same, and then you apply the one parametric H principle, so the fact that this map is an isomorphism on pi 0, which uses pi 1, 2, and then you'll deduce Smale's sphere version from this. Okay, so these are some examples, and now let's see what we can do. Questions? Okay, so the key point is that if M is open, then there exists a core for M of positive codimension. And what do I mean? Let's just agree that this means that there exists an isotopy of M such that R0 is the identity, and for all open neighborhood containing K, we have that this isotopy puts all of M inside U for T large enough. Okay, so this isotopy shrinks everything in a neighborhood. That's M. This is a core, and there exists this isotopy RT that will bring all of M into an arbitrarily small neighborhood U of the core. Okay, so let little f capital F be a monomorphism from Tn to Tn, and this is the same. This is the same data as a section from M to the one jet bundle of maps from M to N. Because let me just do it explicitly. This one jet bundle is fibered over the zero jet bundle, which is just the product of M and N, and the fiber over M comma N. Maybe I'll say XY. We've already used M and N for dimensioning. The fiber over XY is precisely the set of linear maps from TXM to TYN. Okay, so this data gives me a section. So what am I going to do? I'm going to apply holonomic approximation. To K and S. So I will leave that, but I will erase the parametric version now, which by the way is proved in the exact same way, just adding the superscript everywhere. So what do I get? I get an isotopy FT, which wiggles K. And then on some neighborhood W, I have some holonomic section, which here is just a map. W to N, smooth map. Such that the one jet of G is C0 close to S on this neighborhood. Okay. So far so good. Any questions so far? Okay. But now you see, if the approximation is good enough, then dg is close to f, which is injective. That means that dg will also be injective. I.e., g is an immersion, sometimes denoted with the symbol, of W into N. Okay, so here I'm using this openness of the differential relation of immersions to conclude that anything sufficiently close to an immersion is also, well, any linear map sufficiently close to an injective linear map is also injective. It's non-vanishing of some determinant. And now that's it. So then set, I don't know, H to be G, but of course I first need to bring all my manifold into that neighborhood U. So first use a T, and then that's not quite good enough because that brings me to a neighborhood of K, but G is defined on the wiggle neighborhood of K. So put F1 in between, and then for T large enough, this is an immersion from N into N. And if you want to do the parametric version, you add a superscript everywhere. That's the end of the proof of the first theorem. Okay. So I'll give you a minute to digest that, and please do ask any questions.
Sorry, how do you know that there is a T large enough so that it works for all points?
I just need T large enough such that RT of M is contained in the neighborhood F1 inverse of W. And by my definition of a core, that's true for T large enough. Okay, you can imagine U just set that to be U. And then pick T large enough so that I land in there. More questions?
What was the definition between open and open?
The definition, great. So here we're using a fundamental lemma, which said if M is open, which for being connected means that it's not compact or has non-empty boundary. So lemma, if M is open, then there exists a core, A for M, of positive what I mentioned. Okay, so this lemma needs to be proved. It's not entirely obvious. There's several possible proofs. So proof one, pick a proper Morse function and cancel the maxima in the spirit of, there's a general principle by which you can often cancel critical points of Morse functions when they are not essential for the topology. So in this case, you can convince yourself rather easily that if M is open, the top degree of homology is 0. And so if those local maxima are not really needed, they're not homologically essential. And so it is plausible that one could play around with a Morse function and actually cancel them. And indeed one can do it. And another possible approach, I mean, you can imagine that M is, let's say M is compact with non-empty boundary and it's triangulated. Okay, so just triangulate it. And now start deleting start deleting some of these faces of the triangulation and push your manifold inside. And okay, you need to have some coherent scheme for doing this, but of course, if your manifold is closed, you can't do it. But if your manifold has a non-empty boundary, you can think of starting at the boundary and then pushing this in, and so then your whole manifold is deformation retracts onto the manifold with this one deleted, and then you keep on going, and of course eventually you will get stuck. But if you do it in a clever way, you will be able to deformation retract the whole manifold onto a subcomplex of this triangulation consisting only of n-1 dimensional simplices. Okay, so
never said that the inclusion of K to M is deformation.
yeah, well, okay, but I don't need it. I just need that property. But in fact, something stronger is true. Like I could.
Is this just an important issue of handle dimension yesterday's?
Yeah, but this lemma was never proved in yesterday's talk. So in other words, if M is open, it has handle dimension strictly smaller than the dimension of M. So thank you. More questions? Yeah.
So if we use the first construction of core, we do need holonomic approximation principle for stratified subsets for positive.
Yeah, but again, as we discussed, like you actually need very, very little about the stratified subset. You don't even need wouldn't be stratified. Yeah, I mean, it's very, very mild conditions on the stratification to make the proof work. More questions? Okay. So now let's do it for closed manifold. And the key idea is that of micro extension and what will be, you see, let me just make a remark, the same proof. The exact same proof shows if I have a differential relation in a dead space which is open and diff invariant, then R satisfies a full H principal on any open manifold. Okay, so you can look at that argument and you can convince yourself that the only thing that we used was that the differential relation of emergence was open because I solved it by C0 approximating a solution, and that it's diff invariant because I said that, you know, because G is an immersion, if I first reparameterize it by a diffeomorphism, it's still an immersion. And so that's just the property that immersions are diff invariant. And then of course I use the existence of a core, so I use the fact that M was open. But the same proof shows that any open diff invariant partial differential relation satisfies a full H principal in any open manifold. So, you know, contact structures and open manifolds, full H principal. Symplectic structures, you have to work a little bit harder, but you know, you can start with this and end there. And whenever you see a open differential relation that satisfies a H principal on an open manifold, if it's open, chances are you can prove it, you know, this way. Okay, but now let's do the case of closed manifolds. Any questions about this? The proof of Smale-Hurt. Closed manifolds. And again, I'm going to do the zero parametric case, and the multi-parametric case is proved the same way by adding pink subscripts everywhere. So what do? So now I have M. I have some smooth map F into N, and the image could be terrible, right? Because I'm not assuming anything about F. But what I am assuming is that I have covering F, a capital F, that is fiber-wise injective. So I have TXM, and I have capital F, and that sends me to some dimension M linear subspace of the tangent space of the target. Okay. So here's the tangent space to N at little f of x. Here is the image by capital F of the tangent space to M at x. And consider the normal bundle, eta. Of x. Okay, so you can think of it as a quotient, or you can think of it as an actual subbundle by any way you want, taking the Riemannian metric and fixing the orthogonal complements if you want to. So what is eta? Eta is a vector bundle over M. And let's call the total space Y. So, of course, there is a canonical way to extend capital F to a monomorphism from the tangent space of Y. Because what do I have to do? I have to extend it to eta, and I can extend it by the identity. Okay, so you can extend F from Tm to Tn to, let's say, G from Ty to Tn. And this is a monomorphism from Ty to Tn. Okay, because here was the tangent space to m at x that I was mapping via f of x, and now what is the tangent space y near the zero section, but everywhere, you can think of it as just being the direct sum of the tangent space to x at m and eta of x. And so, of course, here I can just send it by the identity, and together I call this whole thing g of x. Okay. Is everyone happy with that? And now the point is, M is a core for the total space of eta. M is a core for Y. So you see, or even, I mean, Y is open. Y is open. It's the total space of a vector bundle. So, by what we just discussed, there exists an immersion H from Y into N, and moreover, it's in the right formal class. So the H is homotopic to G. And then you just restrict to M. And you can do it in families. And that's the end of the proof. Questions?
Do all proofs of the H principle for the closed case pass through the open case, or can you
No.
do it directly?
No, so we're gonna so this is in some sense the third proof of this theorem that you see. So Yasha sketched a proof of Samail-Hirsch for closed manifolds using the technique of removal of singularities. Melanie indicated how for some special class of differential relations called ample, you can use this convex integration business to prove H principle on closed manifolds, and neither of those approaches pass through open manifolds. But this one does. There is a general principle for proving differential relations on closed manifolds when you can extend the differential relation to a thickening, and in a key way, when the restriction, the process of restricting preserves the differential relation. So let me just make a comment that this implies that submersions of open manifolds satisfy an H principle, but this technique, which is called microextension, fails. So you don't have an H principle for submersions of closed manifolds. And a key problem is that the restriction of an immersion to a submanifold is still an immersion, but the restriction of a submersion to a submanifold is not a submersion. So some of them you can do this way, but some you can't. Yeah.
So fiberwise injective bundle maps also sounds like an open differential
Right.
relation to me.
Yes.
Could I also apply this remark directly?
To which one?
I'm asking if I could also proves the second theorem just directly if using this remark, if I formulate bundle monomorphisms of a proper codimensional manifold through a differential population, because I don't know, bundle monomorphism still sounds like an open condition to me.
Bundle monomorphism is open, but what we did in the case of open manifolds is we used this retracting to the core. So I don't know, at least with holonomic approximation, how to prove it for closed manifolds without first proving it for open manifolds. In the case of immersions, which I think is what you're talking about, because fiberwise injective bundle monomorphisms is the differential relation corresponding to immersions. Does that answer your question?
I'm not sure but
Okay, maybe we can talk later.
Yeah.
More questions.
It seems to me that you've only shown ISO on pi 0.
Yes, you're right. And so to do it for higher homotopy groups, you get the pink chalk and you put a Z everywhere.
Thank you.
It's nice, yeah. I mean, it's not always true, but it is. If it is a virtue of this theory that if you set it up appropriately, often the parametric statements are no more difficult to prove than the non-parametric statements. I'll make some more remarks, which is that in this case, in the case of closed manifolds, we actually can get C0 close and relative, because in the case of open manifolds, what we can get is C0 close and relative for subsets of the core. You can't, of course, get the full C0 close or relative because you're doing this massive isotopy, but this massive isotopy, maybe I can moreover demand in my definition of a core that it leaves the core fixed. And I should have done that, and then if then it's true that open manifolds still have a core with that stronger property, and so I can get C0 close and relative on the core, and here I'm only using, here N is the core of that open manifold, and so I get C0 close and relative H principal for immersions of manifolds of smaller dimension. More questions? Any other questions? Okay, so this is good. I think I've essentially given a full proof of, result that contributed to a Fields medal. So it's good for a couple. Yeah.
Question. So in the symplectic case, to go from the open to the closed, what exactly would be failing there?
I mean, it's just not true.
Yeah, I know it's not true,
Yeah.
but there would this sort of micro extension technique be failing.
I mean, I'm not even sure how to set up the micro extension problem, but I mean, we could try to think about it later if you want. Yeah. Maybe it's that some manifolds of a symplectic manifold need not be symplectic. Okay, so with my remaining time, I want to now talk about a slightly different application that will come up in the symplectic talks. So you have this one jet space, which again is just the product of the cotangent bundle times R, and here I will have Q the position coordinates on N, and P the dual cotangent coordinates. So the space has coordinates q1 to qn, p1 to pn, and z. And on this object, there is a differential one form written dz minus pdq, which means this dz minus sum I from 1 to n of pi dqi. And we call this the standard contact form. Okay, it's a contact form because it satisfies the property of non-degeneracy, maximal non-interpretability. Okay, and definition. If I have a map, if I have an embedding of a manifold L into the one jet space, such that this form is pulled back to 0, we call this an isotropic embedding. Okay. This non-degeneracy condition implies that if I have an isotropic embedding, then the maximal dimension that L can have is n. Okay, where this m had dimension n, and this one jet space has dimension 2n plus 1. So it has to have dimension less than half. Half is a fractional number. And we will call isotropic embeddings respectively Legendrian when the dimension of L is the maximal possible, and we will call them subcritical when the dimension of L is strictly smaller than the maximum possible. So for example, suppose that I have a section. When is it isotropic? Okay, which in this case is Legendrian, because that is the maximal dimension. Well, we know how to draw a section of the one jet space. It's given by some 0th order information and some slopes p. And what does isotropic means? Well, it means that dz minus pdq is 0 on the image. In other words, it means that p is dz dq, i.e., it means that S is holonomic. Okay, so it means that actually the p's were tangent Okay, so this one is isotropic. This one is not. Any questions about that? Okay, everyone happy? But of course, need not be graphical. I just need the 0th order part to be tangent to the family of slopes. So this, for example, is another perfectly fine Legendrian embedding. And you're going to say, but it has a singularity. It doesn't. This is, so this, remember, is J0 of MR. And what we're seeing here is the image under this forgetful map of M. Okay, so this is called the front projection, and this is called the wavefront. Okay, and if you shine a light on your mug and you look at the inside of a mug, you'll see a semi-cubical cusp like this. And the reason why this looks non-smooth but is actually smooth, I mean, let's just compute, right? So this here, Z is plus minus Q to the 3/2. So what is P? It's dz dq. So P is, all constant for 1 is plus minus Q to the 1/2. So if I actually draw it in the QP plane, this looks perfectly nice and smooth. And so what's happening is in the QPZ plane, I have some smooth curve that just turns around like that. And if I project it here, I see a cusp. But if I project it down there, I see a parabola, and the curve is actually nice and smooth. So cusps in the front projection are your friends, and they just correspond to smooth points. Okay, there's other singularities of wavefronts that are allowed. Not all of them are allowed, but definitely cusps are fine. But what's important about isotropic embeddings is they are tangent to their P coordinates. Any questions so far? No questions? Okay, so now what is a formal isotropic embedding? So isotropic embeddings, let's just say from M into the one from a manifold L into the one jet space of a manifold. If you know what a contact manifold is, then you know how to, well, okay, let me just say. Let me just say a contact manifold is a manifold of odd dimension equipped with a hyperplane field. I'm going to just say the coorientable makes so everything will be coorientable in this talk, such that this is the kernel of a one form satisfying the maximal non-degeneracy condition, which means that the hyperplane field is maximally non-integrable. And so in general, an isotropic embedding into a contact manifold consists of a smooth embedding, which is tangent to the contact distribution. And formal isotropic embeddings are going to be any smooth map, any smooth embedding plus a rotation of the tangent map such that at time one, the image is contained in the hyperplane field, and moreover, the alpha restricted to that subspace is 0. Okay, so there's an obvious map from here to here where ft is constant, and so again I've decoupled the function from its derivative, and I just need to make sure that the derivative can be rotated, can be deformed to a fiber-wise isotropic linear map. Any questions about what an isotropic embedding or what a formal isotropic embedding is?
Why would it be a bad definition to just ask that it covers, there's some map that covers a smooth function which takes TL into the hyperplane field?
Say it again.
So why would it be a bad definition to define the formal embeddings as a map that covers a function that takes the tangent space of L into the hyperplane field? Why did you need this isotropy?
Well, the best answer is that this is the definition that makes the H principle true. So, like Yasha was saying, often there's several reasonable choices for what the formal data could be. And, we can try to do some philosophy, but somehow this is the correct definition because mathematics works with this definition. And you might want some other definition to be the right one. But if theorem is false for that definition, then this wasn't the right definition.
Maybe what embeddings are not there.
You can talk about isotropic immersions if you want, and that's a separate theorem. But for the symplectic and contact topologist, it is often important to consider Legendre or isotropic embeddings rather than immersions. So this is a theorem that is of greater significance to the field, or the theorem that I'm about to write is a theorem of greater significance to the field.
Maybe a follow-up comment, I guess, is that, you could define something that is like a formal embedding in the sense of what Yasha defined yesterday for Havliger's theorem, and then couple that with something that also puts the isotropic condition in it. But then you're creating too much of a job for yourself, right? Because you're proving Havliger and at the same time trying to make it isotropic. But it's kind of better, well, first make it into an embedding and then try to make it isotropic. But this is good. Maybe.
So if one question, if you don't ask like this homotopy and you just ask like a fiber-wise monomorphism or something like that, I guess there's no reason that F1 would be homotopic to the differential of the base.
Right. Right. Yeah, so suddenly, if you try to prove parametric H principle, then you're going to get into trouble.
Can I ask?
Yep.
I'm not sure if I understand what's possible for this vector space to be both in the kernel of alpha and the kernel d alpha when alpha which d alpha is not good. You have these two conditions on F1 of TL. But
Right.
also it's not in general.
So there's the kernel of alpha. Okay, here so this is where alpha is not 0. And then the alpha restricted to the kernel of alpha is a symplectic form.
Oh yeah. Oh, okay. Yeah, thanks.
So
So it's like a Lagrangian
Yes, it's a Lagrangian index.
Thanks.
Yeah. More questions? Okay, so theorem. When the dimension of L is strictly smaller than n, then there's a full H principle. Okay, so again, notice the dimensional restriction that might be reminiscent of the fact that well, anyway, let me say one word at the end if I have time about that, and let me give a plausibility. I'm not going to give the full proof because it's a bit involved, but let's just suppose that I have let's say L sits inside M, and what I have is a section. Okay. So suppose that I have a section. So what does it look like? It looks like the graph of a function and then a bunch of planes, graphical planes that are not necessarily tangent. So what I can do with holonomic approximation.
Maybe Danny, because like in this case, you're like your M will be now J1. M R.
Yeah. So here N is again the one jet space of M. Thank you. Okay, and so here let's just suppose I have any section. Okay, and so I'm drawing here the section S. And so what I can do is I can approximate this section by a holonomic section in a wiggled neighborhood of L. So now I have some neighborhood. And now I can approximate the tangent planes. I can approximate this not holonomic section by a holonomic section. And so this is now a Legendrian embedding. Legendrian section U from the one jet space run to R, and it's C0 close to S, so the formal data is definitely well approximated. And so now I can restrict S to L. I can restrict S to F1 of L and precompose it with F1 to obtain my isotropic embedding. So again, I'm using the restriction of an isotropic embedding to a submanifold is still isotropic. So it's, if you will, some form of micro extension.
Can you say roughly where you use the rotation condition?
So here, I'm not here because everything is graphical. I've already put myself in a situation in which I don't need to keep track of the formal data. If I were to prove this theorem in full generality, I would have to be very careful with that rotation, and there's some amount of work into getting myself into this situation. But you see, here, everything is graphical, so graphical planes are form a contractible set. No, not much to say. But this is a plausibility argument for why this result might be true. I'm not saying it's a proof, it's not. You need to do some more work, but you can read Kai's book and see the full proof there if you want. There's actually several ways to prove this theorem. One of them goes through this isocontact embedding stuff that we heard in the previous talk. Any more questions? Okay, so I'm just going to finish by hinting at what you could do. So this doesn't work when the dimension of L is equal to n.
Is there a similar theorem for like isotropic embedding simplex?
Yeah, yes, fine. So let me just finish by saying, so now what if I wanted to approximate something and I don't have this extra codimension? So what if I wanted to approximate this by a holonomic section? Well, of course, I can't do it without positive codimension unless I allow myself to escape the world of graphical objects, and then it's very easy to approximate this field of yellow planes by the tangent planes to a curve if I just allow it to have cusps. Okay. And so as I tell, cusps are our friends. So for dimension L equals n, you do have surjectivity on pi 0, and moreover, you can save an H principle for a special class of Legendrians called loose. And what is the deal? The deal is that if you try to do this in families, you're going to have to allow these zigzags to be born and die. But this is not your friend. The birth death of a zigzag in the PQ projection will look as one of these Whitney umbrellas that Melanie was concerned with, and this is a genuine singularity. This is not good. So what are loose Legendrians? They are Legendrians that already have a zigzag in them that you can then use to create as many zigzags as you want so that you can make this proof work in parameters. And so it's one of these cases where you don't have an H principle in general, but you do have it for a special class of flexible structures. The other main example being contact structures, where you don't have an H principle for all contact structures on closed manifolds, but you do have it for the class of over-twisted contact structures, which again are characterized by the presence of some flexibility virus, as Yasha says, that allows you to make it work. And I think I'll stop here.